everything is perfectly fine for our test engineer, but now our test department is loaded with some new tasks, and for example, he now should also do some durability testing of the chassis on the road, and that would mean to him he needs to add a lot more analog inputs, like maybe say 100 more inputs. And of course in his very small unit this is not possible. Another requirement might be that he should also record video in addition. So what does this now mean to our measurement system and to the synchronization architecture? Remember, in the single system we had the backplane with the sync clock and the trigger to synchronize all the modules. Now, since we add a second chassis or a complete second system, we need to take this and distribute it to that system, and this is done over what we call the try-on sync bus to just expand the synchronization capabilities. The try-on sync bus is a LVDS, so a low voltage differential signal, which we use to be as much resistant against electromagnetic interference as possible. The data link is done depending on how we expand. If we just take a passive expansion chassis to get more slots, we hook that up via a PCI Express connection. If we use a complete second system where there is also the PC inside, we do the data link over the Ethernet. So now, how is video done? The video synchronization is also done pretty much the same way, but here of course we've got an external device. So there is a certain try-on module that we use to create a clock for external devices. Again, of course, this clock is completely synchronized to the internal clock. As you can see here, the camera clock is put out there, and then of course the DEWETRON camera has an input where we connect this clock, and then whenever that clock arises, the camera takes a picture. So, as an example, if we, for example, take a sampling rate of 1 kilohertz again, and we want to have 100 frames per second from the camera, then what we do is that of course we have to create the 100 hertz clock here, and that means this clock will arise at AD sample 0 and then at sample 10, 20 and so on. Finally, we will get a picture after every 10 samples or exactly after each 10 milliseconds, which is finally our 100 frames per second. If we want to hook up more cameras, then we also provide a special hardware box to make it easy for cabling and for setting up the complete system. So now our test engineer is faced another new task, and his task is becoming more and more complex. So in the next step, what he should do now is testing the functional safety. And testing the functional safety is something like in all other safety relevant standards. It is crucial to comply to the standards, and also documented evidence must be provided. For the functional safety, put very simply, all mechatronically controlled systems where sensor information is the basis for actions must be tested, evaluated and fine-tuned before the systems can be released for mass production. Now a few more words. As per the ISO 26262 standard, at the first step, the systems and vehicle functions are described by items, and each item is then matched with its potential hazards or malfunctions. The simulation of such malfunctions in specific driving situations enables the OEM to do a classification corresponding to the automotive integrity level, or in short, ASIL. There are several levels, like starting from ASIL A, which means very low hazard, up to ASIL D, which is high hazard, or it is related to QM, and then it means it's not a safety relevant issue. Finally, how is this classification to ASIL achieved? It is done according to the severity of the potential hazard, to the frequency of the driving situation, which is also called the exposure, and to the controllability for the driver. With the rising ASIL, also the safety requirements for the corresponding system will increase. As an example, I brought here the brake control system. In the brake control system, besides the controllability which I mentioned before, we also need to measure the lane deviation, because we said depending on the hazard being high or low, the ASIL classification is done. Now of course it depends if, for example, my jaw rate sensor is failing and the ESC is taking over. Is it a big problem if my car leaves the lane by 1 centimeter? No, this is no problem, so would be a very low risk. But what if the car would leave the trajectory by, let's say, 2 meters? That would be extremely critical, of course, because either we would completely leave the road or we would be on the opposite lane. So very dangerous. And this objective data that is taken combined with the exposure is finally used to define the ASIL level. So much to that one. The system would look like this. We need the data acquisition system, then very precise position sensing, and then canvas, and as mentioned before, a new thing is involved. We need to have XCB to also record ECU parameters. And XCB might also be used to simulate the errors, to inject the errors into the data stream. So now, the most complex task possible of all that testing procedures is ADAS testing with multiple
잠깐만 녹음하고
vehicles,
말려고 했는데
or could also be
드라이버
one
어시스턴스
vehicle and
시스템
maybe
설명이
some
나오다
pedestrian.
보니까 그냥 끝까지 녹음해야겠네요.
If this is the case, then we need to, of course, also synchronize the data acquisition systems from 2 or more cars. So we need to have online data transfer and, of course, perfect sync between those. What would be an example for that? We could have ACC testing, FCW, AEB, or some pedestrian protection, or let's say a crossroad assist, things like that. So in a multi-measurement system setup, how do we do the sync? In this case, we have a module that is creating the sync clock and the trigger. And this module is either a try on base or a try on timing. And those modules, they take the GPS, PPS, which we usually get over the ADMA inertial platform, and then here create the sync clock and the trigger for the backplane. We do the same here, and how the trigger is created is very simple. We just use the PPS to create this trigger. And that means that this system and these systems always start their acquisition at the full second. And since we know it started at the full second and we have absolute time here and here, it is very easy for us later on to combine and merge the data. If we have an online data link, like Wi-Fi for example, this data can even be merged online during driving, right during the testing.
이건 좀 의문이 있는 게 위성의 이제 GPS 시스템이라든지 그런 걸 이용해서 그 위성 신호를 이용해서 싱크로나이즈를 하겠다는데 그럴 경우에는 그 상호 시스템 간의 싱크로나이즈율이 어느 정도 되는지 분명히 지터가 발생할 우려가 굉장히 많기 때문에 확인이 좀 더 필요한 부분인 것 같다.
So now I want to do a case study and explain a little bit more about the FCW and the AEB. So first, the FCW, which is the which is the forward collision warning. What is the idea of the FCW? This is pretty simple. Basically, this is our car that we want to test. This is some other car, and the idea is let's have some sensors in this car and monitor the preceding car. Then take this sensor information into the ECU, do an analysis in the ECU, and then if there is a potential danger, warn the driver. By example, a gong, some optic information, or some haptic information. The major task for the testing system is to determine the TTC. This is the time to collision when these systems are reacting in the car. One more word regarding this testing is in the USA, the NHTSA developed testing procedures for the FCW. And of course for the USA now any car anyway needs to be tested according to these procedures, but most others also use the NHTSA procedures for testing FCW systems. And maybe also mentioning the NHTSA is recommending to use the DEWETRON system for such kind of testing. Then the AEB is basically pretty much the same as the FCW, but on AEB the makers did the logical next step so that the car is not only warning the driver, but if the driver doesn't react, also does the next step and is braking on its own.
이 시스템을 처음 이용한 유명한 회사가 이제 볼보 같은 경우에는 저속에서 차량과 추돌이 일어날 경우 알아서 오토매틱 브레이킹이 들어가는 시스템을 얘기하는 것 같다.
And now I would like to show you a short video how such testing is roughly done. So you see that is working. Now this is a test which is failing. So of course usually some kind of soft target is used for this kind of testing. The system that we use for that is a combined system of a DEWETRON data acquisition system, of an inertial GPS platform from company Genesis from Germany, and the robot systems from a company called Stehle in Germany. So we are partnering and teaming up here to provide a complete testing solution for the user. Of course, our combined testing solution is also fully capable to do the Euro NCAP testing according to their standards. So now I would like to show you a little bit which maneuvers the NHTSA is defining. Basically what we always have is one car that we test, it's called either the vehicle under test or the subject vehicle, our green car, and then we have this red car, which is a principal other vehicle. And in this first test procedure, what is happening is that our subject vehicle is encountering a stopped principal other vehicle on the road. In the test number 2, the SV is encountering a POV which is braking. So that means at first both go with the same speed, and then this car starts to brake. The third test that is defined is that our subject vehicle is encountering a principal other vehicle which is just driving slower. So this doesn't seem to be so complex for the testing. But maybe let's have a closer look how it really is, because you will soon see that there is especially one really big challenge for the testing systems. So which signals do have to be measured according to the NHTSA? we do have position and trajectory of both vehicles. We need the speeds, we need the yaw rates, we need the deceleration of the BOV, we need the warning signals, acoustic and optical, and the request of the warning signals. And then, out of all that, we have to calculate some parameters which you can see here. This is, for example, the distance of both systems. Then we have the lane deviation from the center line. Obviously, we have the time to collision. And then also compliance with testing criteria. For example, in the subject vehicle, the speed needs to be constant for at least 3 seconds before the BOV starts braking. And then we also have start and stop trigger criteria. For example, start the test when the distance is 150 meters and stop the test when the FCW is activated. So if we now take a closer look to the test 2, we figure out that we need the brake signal of the BOV for calculation, because one of the conditions is that the speed of our subject vehicle cannot deviate from the nominal speed for more than 1 mile per hour for a period of 3 seconds prior initiation of the BOV braking. This brake signal that we need is available on the FlexRay or on the CAN bus of the BOV. And only because of our sync clock technology, this is no problem for us to take this signal to transfer it to the subject vehicle and have it fully synchronized with the data of the subject vehicle. Of course, we also need inertial data, and here it's also especially important that the position data from the INS GPS system is 0 millisecond delay. Because what